think my new policy is not going to be to ask for questions. If you have a question that's short, you can just shout it out. So, the next talk is by Ingrid Fay, about achieving phase iterated SPMs by SDP.
Hi all. So I'm going to discuss achieving the Bayes error rate in stochastic block model by SDP robustly. This is work done by my office mate in GFA and my advisor Yudong Chen. Since they cannot come here due to traveling reasons, so I come here to present this work for them. Let us just get familiar with the stochastic block model. It's a little bit different from the previous talk. So there are n nodes, and they are partitioned into two unknown clusters of equal size. So there is also assignment vector sigma star, taking value +1 and -1 and of length n. Because there are two equal clusters, the summation of each component of sigma star is 0. So the observation we have is a graph adjacency matrix of size n times n and taking value 0 and 1. For each aij, if sigma I star times sigma j star equals to 1, meaning the two nodes are in the same cluster, then aij follows the Bernoulli P distribution. If sigma I star times sigma j star equals to -1, meaning the two nodes are in two different clusters, then aij follows the Bernoulli Q distribution, where Q is strictly less than P. Our goal here is try to recover sigma star, or the Y star, which is a matrix version of sigma star. So sigma star times its transpose from the observation, the adjacency matrix A. Okay. Just to give an example of this model. So here we have the first 500 nodes in the same cluster, while the last 500 nodes in another cluster. And the left part here is the adjacency matrix, with the blue color indicating there is an edge, and the lighter color there indicating there is no edge. So even within the same cluster, it is possible that some edges are not present. Well, across different clusters, there might be some edges still. The right plot here is the Y star, the sigma star times its transpose, the matrix that we wish to recover. So the positive one here means is the blue area, and the negative one is the lighter area, the area with lighter colors. Okay. So the procedure we propose to recover this sigma star or the Y star is solving this SDP here. So we try to maximize the inner product between Y and the adjacency matrix A. So Y here is an n times n matrix. The constraints that we put into this SDP, the semi-definite program, is this Y being positive semi-definite, meaning that it is symmetric and all its eigenvalues are non-negative. Y inner product with J equal to 0, meaning that the J matrix is the matrix with all entries being 1. So this constraint here, Y inner product with J equals 0, simply means the summation of all the entries of Y is 0. And we also require the diagonal of this matrix Y being 1 always. To say the method, just let me define one more notion about the superlevel set with respect to Y star. So a set is in the superlevel set of curl YA, if and only if the objective value of this Y is greater than or equal to the objective value of Y star, and Y being feasible. So just to estimate this Y star, we just choose any Y hat that is in the superlevel set. So the way we try to estimate this sigma star, we simply pick the top eigenvector of Y hat and then take the sign of that. So that becomes our estimator of the sigma star. We denote it as sigma hat SDP. So in the past, let me just explain what we mean by Bayes rates. So here in the past, the left-hand side of this inequality indicates the yeah, I know. The left-hand side of this inequality is like the this minimax rate is known as the Bayes rate. So just try to explain the notation here. The inner quantity, the arrow sigma hat and sigma, is a fraction of disagreements between sigma hat and sigma with a global flip. So it's the difference between sigma hat or plus sigma and minus sigma. So we take the smaller of the two. And the set we take over is the set of all possible label assignments with two clusters of roughly equal size. So I star, okay. So this is the Bayes rates. The right-hand side shows the lower bound, which is of an exponential form. And this is like the goal that we wish to achieve. Here, the I star is a sort of is a Ren-Yi divergence measure of all the half between Bernoulli P and Bernoulli Q. You can consider it as a sort of a signal-to-noise ratio or a measure of distance between these two distributions. So the main results of this paper, of this work, is showing that this SDP approach actually achieves this lower bound. So if this n times I star is greater than some universal constant, then there is two universal constants such that we actually achieve the lower bound both in terms of this original, both in terms of the matrix version, the y hat times y star of the entry-wise one norm, meaning that the sum of the absolute value of all the entries of this difference. Note here, the right-hand side is actually taking the integer part. So as long as the quantity inside the bracket is below 1, then it's actually 0. So in that setting, we actually achieve exact recovery. For the original version, for the sigma star, the right-hand side quantity actually matches the lower bound when these n times I star goes to infinity. Let me just explain what we mean by robust here. So we're also trying to say that this SDP is robust to monotone adversary, meaning that if you add some edges for the edges within the same cluster, or remove edges for the nodes that are in different clusters, if you allow these operations, then this SDP will still attain these two exponential type bounds. But so it is robust to this monotone adversary. Well, some spectral method or other algorithm may be fragile to this monotone adversary. To establish these bounds, so we use they use a novel primal dual analysis, meaning that there is not just using a, so we use a dual certificate that constructed in the past, but not use that to certificate the optimality of y hat, but use that to analyze these two quantities. Finally, I just want to mention the framework provided in this work can also analyze this Z2 synchronization problem, and as well as the sensor block model. So just for more information, you can check this archive preprint, and we will also have our poster in tonight. Thank you.